Okay, let's wrap up our talk about molecular orbital theory. We've done the bulk of what I wanted to cover in terms of molecular orbital theory. And really, it's just that, drawing the orbital diagrams and working through some stuff like that. Okay, remember we talked about oxygen and it being paramagnetic because of the unpaired electrons in that anti-bonding orbital, but we still has a bond order of 2 and all of that fun stuff. Um, but let's take a stab at trying to explain this. Remember, we talked about ozone, we talked about delocalized bonding, and we talked about resonance. Remember, we said that um, ozone has good Lewis structures that look like this. However, it's not correct, right? I mean, it's a valid Lewis structure, but it's not exactly what ozone looks like because the bonds on either side look like they're different, but experimentally they look the same. Okay, they have the same bond length and the same bond energy. However, when you draw the Lewis structure as a double and a single, you wouldn't expect that. Okay, and we said actually that this is because these are 1.5 bonds, because we have 3 pairs shared over 2 connections. So this is 1.5 bond. Okay, so what we're getting at here, what I want to impress upon us is that the reason this happens, or really why, maybe not why, but how this happens, that's a good word, how this happens is because of the molecular orbitals that are involved. Okay, so let's take a look at ozone in terms of molecular orbitals. All right, now what's happening here is we need to look at compounds through the glasses of valence bond theory and molecular orbital theory at the same time. Okay, so since every one of these oxygens in ozone has 3 electron groups, we're going to say that every oxygen in ozone is sp2 hybridized. Okay, what that does is it lets us explain some stuff. We have a sigma bond formed between 2 oxygens on each side of the central oxygen. Okay, each oxygen on the end has a lone pair in an sp2 orbital, and the oxygen in the center has a lone pair on an sp2 orbital. So what we've explained out of our Lewis structures is the lone pairs on the outside, 2 of them, and the center, one of the bonds of the double and one on the other side. Okay, but it doesn't explain one of the bonds here and one of the lone pairs. Okay, all we've done is explain the sigma bonds. We need to figure out where that pi bond is coming from and where that lone pair is coming from and how we can put those in orbitals. And if we remember, that pi bond is due to having a leftover unhybridized p orbital, which we do. And if you remember, if we have sp2, we're going to have one unhybridized p orbital there. Since we have 3 atoms, we have 3 p orbitals to work with. Okay. And remember, if we have p orbitals, we can form pi bonds, but they only form from overlapping sideways. Remember, this is the way you make pi bonds. Sideways overlap of 2 parallel unhybridized p orbitals will get us there. Okay, but we have 3 unhybridized p orbitals. Well, that'll work too. If we take 3 unhybridized p orbitals and overlap them all together to make molecular orbitals, right? We're going to take 3 orbitals in. This is going to give us 3 orbitals out. Okay, and I wrote where my picture is. God dang it. Okay, 3 in gives us 3 out. Okay, what happens here now, if you put 3 in, okay, we're going to get 3 out. We get what we expect, a bonding orbital. There's 2 electrons in there. The bonding orbital covers all 3 atoms, and it's above and below. This is our pi bond. Okay, we call this pi bond, pi bonding, however you want to think about it, but that's the pi bond, and it's shared among all of the atoms. Okay, we also, because of that, we get an anti-bonding orbital, and here are anti-bonding orbitals empty, which is good, which is why this happens. Okay, now because we get 3 orbitals out, we get 1 extra orbital that we didn't get before, and that's called a non-bonding orbital. This is our lone pair. And if you look, our lone pair orbital has a node on the central oxygen, but is present on each end. So the lone pair is present on each end, but never in the middle. Okay, and so that's what we're seeing with ozone. We have a pi bond that covers all 3 atoms. We have a lone pair on each end, but never in the middle, and we have an anti-bonding orbital that's empty. Okay. And really, the only huge thing I want us to get out of this is to remember that molecular orbitals explain the resonance, explain why we have delocalized bonding. Okay. We can take this to an extreme and think about benzene. Okay. We talked a little bit about benzene before, maybe when we talked about resonance. But if we look at it, every one of these carbon atoms is sp2 hybridized. So every one of these carbon atoms has a leftover p orbital. So we have 6p orbitals in, means we're going to get 6 molecular orbitals out. And because they're p orbitals, we're going to get pi molecular orbitals out. Remember, we said there's 2 different resonance structures for benzene, and it's because they can share all the way around. And what's happening is we're getting molecular orbitals that look like this. This is a picture I stole from our organic book. Don't stress about it, but they cover multiple atoms. You end up with 3 bonding orbitals and 3 anti-bonding orbitals. All the electrons are lower energy in the bonding orbitals, and all the anti-bonding is empty. So this is a very stable, low energy, good situation. Okay, but all this red stuff I've said before, right? You need to be able to do a molecular orbital diagram, describe what the molecular orbitals look like, how you make a sigma bond, how you make a pi bond, what a sigma bond looks like and a pi bond looks like. Can you pick these guys out of a lineup, right? Can you draw a molecular orbital diagram? Make sure you have an axis that's labeled. Make sure you have your bonds labeled, your orbitals labeled, and do your follow-up questions. All I'm expressing in this video is I want you to be able to look at something and say, oh yes, this is doing resonance, and the resonance happens because there's molecular orbitals, okay? The molecular orbitals cover multiple atoms, so the bonds cover multiple atoms, okay? The link between molecular orbitals and resonance, okay? If you need me for anything, I'm here. Feel free to ask questions, and I will catch up with you later. Have a good one.